Congratulations, you made it. This is week 8 of this class on functional analysis. And tonight I am in my office at Central Paris where I will be holding these office hours for week 8. During this week we talked about modeling. We started with a membrane attached on the boundary, and we saw the equations that govern what happens with this membrane when you exert a force, a vertical force on the membrane. I don't really like the word govern when it comes to modeling, because the model doesn't really govern what happens. It's a model. So we start with a situation. We can try to understand what are the key components of this situation, what is the context, and based on this context, we derive a model. So even though the term which is used very often is govern, I think that it's really a model that approaches what happens when we exert a force on the membrane. And we derive some equations that we studied, and week 8 is all about using these equations and using everything we saw in this class to prove that the equations, the system of equations, the system has one solution only, and that the solution to the equation is continuous with respect to the data, which is important if you think about it, because you never really measure the force, or you really never measure the parameters. What you have is an approximate of these measures, and therefore, if you have a solution that does not depend continuously, from a physical point of view, it would really be a problem. So you can see that modeling is important. Finding the solutions, the existence and uniqueness of the solutions is important. And as important is being able to simulate, therefore compute the solutions numerically. And we used what is called finite element methods to derive numerical simulation for this problem. And I just wanted to say that based on this course in functional analysis, there are some developments, some additional modules we could actually do, or actually there are some books about things that we could read, or additional MOOCs that we could follow. And I just would like to give you a few hints on what you could do next if you're interested in functional analysis. And one thing, obviously, is a numerical simulation, a numerical approximation of the solutions. There is a whole, there could be, basically one could draft an entire course on finite element methods and numerical simulations. Numerical simulation being a little bit wider than finite element method, which is one of the possibility to compute solutions. What elements to choose, what is the speed of convergence, how this relate, and what you will use then is these functional spaces that we define, because you will see that the elements you choose will depend on the kind of solution you expect. If you're in H1 or in H2 or in L2, you will choose different types of elements. So it is important that you understand functional analysis to actually do a numerical simulation properly, and to see what is under the hood, and possibly tweak the numerical simulations if you need to. Another thing you could do after this class is actually go more deeply in what is called spectral theory, which is finding the eigenvalues. Now, and eigenvectors. If you took linear algebra, which I believe you did before taking this class, you've seen that for matrices, you have what is called an eigenvalue. I mean, you have a matrix A, and you can look at, you know that an eigenvalue lambda of this matrix A is a number such that AU equals lambda U, where U is the eigenvector. And it's quite important to actually look at these eigenvalues and eigenvectors. They play an important role in many parts of physics, including vibrations. And for a matrix, you know that if you have a dimension n, an n times n matrix, then when you are in the proper setting, then you will have n eigenvalues that are counted with their multiplicity. and proper setting meaning maybe you have to look at complex eigenvalues as well. But in any case, you have a finite number of eigenvalues. In the case of operators, which kind of generalizes matrices for infinite dimensional spaces, then you're also going to have eigenvalues. And you possibly will have an infinite number of eigenvalues. And that is what we will have to see is how do they, where are they? I mean, are they going to all cluster at one space? In one part of the real line? Are they going to be complex? And if so, are they going to be on the left-hand side, right-hand side, with possible implication of what's going to happen? This is called spectral theory, and that is definitely something which is interesting to look at and could be a further development for this class or for additional MOOCs. Something else that you could be interested in is looking more deeply into control theory, which is quite interesting from a mathematical point of view, also for the engineering applications of the control theory, and which uses functional analysis and even spectral theory quite often. Something else you could look at is what's going on with partial differential equations themselves. And what do we have when we have nonlinear PDEs? And nonlinear PDEs, very often you have to kind of linearize around some points, and sometimes you can't. And in any case, the whole PDE concepts and concepts around PDEs rather is quite interesting and would be a possible next course you could be interested in looking at. And of course, there is all these tools that we've developed. Pretty much for every single one of them, you can go more deeply into these tools, and you could study more distributions. You can study more these functional spaces. You can also study in very deeply topology. So all these tools can also be developed, and if we had more than 8 weeks, we could certainly do more in terms of going further in this class, as well as going deeper in the concept that we've covered. So I hope you enjoyed this class on functional analysis. I would like to thank you all for the feedback we received, and I think that with all the feedback we received, we'll be able to create an ever better MOOC next time. So thank you very much for it. And I would like to thank you very much also all of the people who worked with me on this MOOC, and Anna, Kayum, Pauline, and of course Caroline, who did a wonderful job when it comes to the whole technical aspects and pedagogical aspects of this MOOC. Before we close these office hours and this MOOC, I would like to just talk a little bit about the logistics. Regarding logistics, as you know, you have until Sunday night to turn in the quiz for week 8, and then you have until November 16th to submit, to turn in your final exam, which is, I think, pretty interesting. I mean, that's my feeling. I think it's a pretty nice final exam, and thank you very much, Anna, for drafting this exam and writing up this exam. I would like also to mention that you have until November 16th. I would like to mention the fact that right after you submit, right after the deadline, you will be asked to grade your fellow classmates' work, and it's important you do that. You will be provided with guidelines about grading, and of course a correction about this exam. This being said, again, I would like to thank all of you for participating in this MOOC. I would like to again thank all of the staff for helping with this MOOC, and I hope you enjoyed it. And I wish you a very good final exam and a very good end of this MOOC.